Good morning. In the village of Boulder, Colorado, I've been lucky to be allowed to work on things which would be interesting so long as I don't stray so far away from the interests of the measurement organization for the United States National Institute of Standards and Technology. One important thing which has happened over the time in this tall building and in its thing is that some changes are occurring, have occurred, and the most important is that I have found in these later years that retirement is pretty nice, and the joy is that Dr. Juni has taken my world and made it have a higher speed and higher clarity. What I can tell you about is interesting problems in finding money for science within the United States, or I think perhaps even more interesting is being a participant in the transformation of a building into an operating organization which, with no history whatsoever, but with a gap of 4 years, has twice produced lightning in the city of Boulder, 3:30 in the morning. By the telephone. There's some young people here. One of the joys which I hope you will experience is to be the guides and operators of people of this in your own experience. Boulder came into the world as a scientific thing, actually a little by design. It's the same as our Soviet colleagues had in their Akadem Gorodok outside Novosibirsk city. A few years later, we had the chance to have that building that I showed you. We had a chance to have an absolutely glorious life in the.
Excuse me, I'll just adjust this picture for you.
In the city of Boulder and the surrounding mountains. We could see some evolution of things. My children, I think, insisted that the reason that the cocoa house was no longer available was their memory that the cocoa was too hot. It was possible for us to have an absolutely delicious personal life environment. Due to my wife's efforts, we had the tradition beginning in 1981 when the frontier with China had just freshly opened. Then every few years, a new team of colleagues, and I'm here to say with a little sadness that this colleague Scott Diddams, this colleague David Jones, are not able to join us today, even though they played a major role in what I'm going to tell you. There's some things don't work so well, and I think the good Lord has seen fit to give us skills in different areas, and so my business is trying to think what would be interesting to know about. And we know in physics that there are different kind of interactions. There's electricity, and there's magnetism, and there's energy associated with a rest mass, so-called strong interactions. And it's quite interesting to wonder why they are the size that they are. And if you start asking colleagues about this, it's approximately the situation that one says, well, we have confidence in these equations that we have, but I can't tell you anything why the relationship between electricity and magnetism is 137.00339998, plus or minus 5 in the last place. Fine structure constant, we don't have a clue. So how are we going to make progress to figure out all this darkness around us? So I would say, if you want to understand something, you should find the sharpest tools that you can find. So I think everyone can understand that lasers are not a bad toy. You can get money for research that way, for example. So you should go to your laser optic tool store. And one of the things which you should do is to pick up an aspect of those tools which has the right scaling. For example, if you measure the intensity, the scaling of your precision will be with the square root of time. And we can all dream to live long enough, but if you would measure frequency, we can count how many waves have come in some time, and we get more waves, we have more resolution by the factor that we increased it by. But as well, we can make comparisons in the middle so we can get a square root. So we have a measurement number to the 3/2 as the way the resolution grows. And there's no other game that grows that way. So the gap between this realization and this comb tools is what our story is about today. How do you finally find out how to use these tools? The first part of it is how do you make them? And the carrot at the end is that if you have 15 digits, you might find something interesting. And so I would say this is something like a great brand new highway, just raw dirt on the side, plenty bright lights, still some traffic barriers, and who knows where it goes. Now, this business about clocks has been attractive and has brought some of the most clever guys. Now, think about the gentleman that invented this. I suppose it was a gentleman because of the epoch. And the issue is that we have a mechanical clock, and the spring gets weaker as it's turning and turning, unwinding. But to get a constant torque, wouldn't it be clever to use this thread and go onto a larger and larger radius? So now as it spools itself onto there, we have less force in the cable, but we have a longer moment arm, so there's a first order compensation. So he probably gets one credit with his wife for coming home late that night. He said, "Oh, that was so cool today. Let me tell you what I just figured out." Now, in the few centuries later, our own Huygens, optician par excellence, was playing with this kind of structure, balance wheels. This is going to spring back and forth in the two directions, as you know well, if you were lucky to be old enough to when we had these kinds of things, and not just transistors inside a can. And what's important from the measurement science point of view is the orthogonality of this rotation dependence from some other environments, such as swinging pendulum. Pendulums are going to be just terrible to put on a ship. But on the other hand, in that epoch, one of the most important measurement issues is to know what your longitude is, because there's islands out there, and in the night, when you have all these spices and gold and things, and you're going to be either a billionaire or a goat, depending on whether you crash your ship on this, it was very helpful to know how far you'd travel. This has little tuners on it. Now, we can change them radially. What that will do is change the moment of inertia. So how long does it take for one cycle? That's how we adjust the timing. And to make it so that it doesn't matter if we shake this thing in any direction, we can change these in a differential kind of way so that no torque comes with the acceleration. Well, nearly 100 years later, John Harrison, after probably using half that time building clock after clock, was able to claim the longitude prize, although there was, as you probably know, some pretty tough controversy and hard to get the check to the bank. But it was still incredible precision, 4 × 10⁻⁶. Well, now we have lots of realizations. Here's some ones from history. Atomic clocks now, this was some years ago, 7 centimeters long. Now it's just as small as one's thumbnail. What part of my story is going to be about is to find the just right tech. And here is something which I think is what you would say is cost effective. It's a sweet spot in the technology development. It delivers a better performance than you need, and for the price of 2 persons at McDonald's, you can have this for your home. In the United States, we have service by a National Bureau of Standards organization. In Europe, we have service complements of our counterparts in Braunschweig in Germany. So now what is a clock? So in our antiquities, we had a solar system, and we had some boy of our family, and his job is every day to record one mark on the wall, and we can keep track of how many days we've had, and finally some calendars will come. And as I mentioned, we've had pendulum clocks, and by gearing down the motion of this, one can have a pointer which is showing. In 1960s, radio frequency transitions between magnetic levels in atoms, such as cesium atom, became possible to explore using the technology that was developed for quite another purpose in the middle of the 1940s. And it was possible to interrogate these transitions and with electronics to resolve the zero crossings. This has evolved now in a continuous stream to what are called fountain atomic beam clocks, where atoms can be collected, given a boost, pass through a microwave cavity, go to some apogee, fall back through. There's two interactions, and one can enjoy these fringes that were the basis of a Nobel Prize for Norman Ramsey. The pioneers in this work are the B&M, was called LPTF in those days. And by coming as the second ones, the NIST has been able to make a pretty nice clock. Now what Jun Yi and Ted Hench and plenty of other people are interested in these days is to try to use appropriate energy levels of some atomic system. And these now have a frequency which is related to the microwaves by a power around 100,000. And so that's such a high frequency that we're going to need a new technology to measure it. Here's a picture of one of the first of these optical frequency standards. This is a methane stabilized laser, methane cell, a helium neon cell there. This is actually in an old gold mine when we were trying to measure the speed of light. My now deceased colleague, Dick Barger, and I are now in the laboratory trying to refine this technology. What was interesting about this was the sharp peak that came in the methane spectrum, which was completely foreseen and hidden within some equations, but shows up in the laboratory in a way which is completely convincing. And the line width of that transition can be made less. It's only fixed by the transit time, an uncertainty principle. So here's some effort by Christian Bourdet and myself and Kyoji Uehara and me to improve the resolution of this. And one way to get this longer interaction time is to have larger beam. Another way is to build an apparatus which can be cooled to liquid nitrogen. One of the things I'd like to just note is that this very much was in the do-it-yourself epoch. There's no store that's selling electronics. Although these look rather professional, that's version number 3 of my design that's made by a company. Here's these high voltage drivers, which are made in our shop, and by now, in any catalog you can find the logical progeny of this. What we came to is high resolution at some good level. It was a kilohertz level. This particular splitting is 2 kilohertz, and it's associated exactly with what Professor Glauber had just mentioned, which is the recoil, the momentum that's carried by the light. And when you absorb in the ground state, you go into an excited state, and there's a velocity shift. And that velocity shift then changes the absorption frequency if you view it in the opposite direction. So we enjoyed that hugely. But my topic really is about standards, so let's come back to that. If we say that the reproducibility of our new system is completely good, and why don't we all change over to it, clearly 2 problems come up. One is that there's a team in Japan, a team in Germany, a team in France. Everyone has their own preference. Another one is we have to make contact with the past. So that's only technical thing, so let me talk about it. Here is an interferometer with flat plates, a Fabry-Perot's interferometer, and it's optimized for these fringes that can be seen of what had by this time become the standard, a krypton transition. And here is, with the same mirrors, scanning under frequency control what the fringes of this new system were, and I think you can see which system you would prefer to work with. Even though the accuracy could be as high as 4 × 10⁻⁹ for this krypton, if you're going to check systematic things, you're going to need many units of 300 seconds. That krypton line was actually accepted in just 1960, and a comb was used previous to that. Now, this is a special kind of comb, and you might not have chosen that language, but engraved on this prototype meter bar of 1988, there's actually marks at 10 centimeters. And around 10 centimeters, there's 1 millimeters. And then at the limit of the engraving, which they had, there's 100 microns marks. So this has just the same joy that we will later appreciate for the optical comb. That is to say, we get a huge distance, and then we make little analog measurements around some marker. This kilogram, I'm shocked to find it's a picture available of it sitting out in the air, since now we have optical methods to replace this, but we don't yet have a way to replace the mass standards. So let me talk then about the fundamental source of our being able to do science, that is to say, to be able to make measurements. Now, there are a few cases where you can compare two things that are practically the same, say energy levels of one atom with different kind of energy levels. But ordinarily, we have to make measurements against the standard. The standard could have been the arm to elbow to fingertip of some ruler in the city of Braunschweig. This meter bar convention was taken in 1875. By just a few years later, Albert Michelson was trying to do interferometry, and indeed successfully. In fact, it brought him some recognition by this society in 1907. The meter bar served us well from the 1800s up until 1960. There was no serious competition when you took into account the trouble that it would be to change the definition. But finally, the krypton lamp that I showed you, which in fact is not as good as a laser system, it was just okay until that time. The methane stabilized laser was more than 2 digits better. So this transition came in 1960, and a new transition that I'll speak about in just a second came in 1983, in which you can say the meter was demoted. It no longer is one of our base standards. So if we used length bars, length depends on interatomic distances, quantum mechanics, electricity, and magnetism. Whereas if we talk about time, then we have the days, and then people saw that storms produced variation in the length of the day, so let's use a year, but now 1 year is terribly slow clicking for your clock. Cesium was adopted in 1967 for the same kind of reasons. The cesium fountain clocks now perform just about 1 × 10⁻15, and the result is that every clock which we can make now, whether it's in mercury or whatsoever other thing, even though internally its performance could be so high as 10⁻17, even 10⁻18, its accuracy, the knowledge of its frequency, will never be better than 10⁻15, because the standard of time is this cesium transition. So the frequency might depend on slightly different subtle things. This is about spacing between lattice planes, and this is about internal energies. This also contains something interesting, this so-called fine structure constant. So let's talk then about making the connection between where the standard is. We're going to have a standard at 919-263-1770. It looks like a United States telephone number. And the target frequency would be one of these new ion sources, or Junyi's strontium, or something like that. It's about 1 × 10⁻15 petahertz. Frequency ratio that we need is 115,000. And how can we ever do a frequency factor like that? Well, I can show you how we can do it as a government plan, how we did it as a government plan. Well, it's 7 and then 2 × 2 × 2, and you'll see in a moment what it looks like. And it's 1 electronic stage and 14 lasers. So here is this picture laid out. Please note this is a logarithm scale. So factor 2 is not a very large motion on this. And here's a bunch of different technologies that did lead us from radio frequency domain, the technology of klystrons, and finally lasers, but every different kind of laser. Let me just try to show you something about what scale we're talking about. Here are 3 lasers that are around 1 terahertz, 1 times 10 to the 12th hertz. And this is what that apparatus looks like. You need 2 people who are extremely dedicated. You need 8 meters kind of length in order to get the powers that are involved to observe the nonlinearities, which in this case are only the factor of 2. So this kind of setup is a little bit space filling. And if you try to look in a more modern setup, not 1972, but 1996, here is the best of these kind of chains that's ever been made. A fantastic engineering effort from hydrogen maser as the reference up through. Each one of these boxes is a little bit the scale of what I just showed you, although some of the lasers didn't need to be quite so long. So here is this 10 microns region. So the National Bureau of Standards speed of light experiment is going to use on this undergraduate formula of the speed of light is the product of the frequency and the wavelength of some radiation. Ken Evenson's team measured the frequency, had quite a few colleagues in it. JILA team measured the wavelength against the krypton in the way that I showed you. That was done by Barger and myself. And the product of those 2 is some particular number. That's simply our finest product, 299792458. And now I take this 8 because that is now what the definition is. It's near to our number. It was a little outside the error limits of our number. But please don't forget there's 50 signatories on the meter convention at this time, and they have 50 people sitting around the table, each representing his own country and trying to negotiate what the number should be. We're never going to get a 0.4 included in that. This gold medal team, well, that was pretty nice. The Department of Commerce recognized our contribution. The thing which makes me really sad about this picture is that Ken Evenson, Dick Barger, Russ Peterson are now deceased, and Gordon has gone into management. So it's so here is the agreement that was taken, consultation with people of many learned societies across the world, to use a definition which makes sense in the primary school kind of understanding that something is flying. Of course, it has to be in vacuum. A physics person would always want that. And then it's in some absurdly small fraction of a second, except that now we actually have timing systems that work pretty well. So this was the redefinition of the meter. It was based on a cooperation of a team of people, and more importantly, or equally importantly, a team of wives and friends. And we need scientific notation to write down how many sandwiches were brought by those beautiful people to make this possible to run in the nights. But atomic clocks are quite popular. Here is an experience that Lindy and I had driving in Hawaii. There's an atomic clock cafe. Well, I better take a picture with that one. There's so many atomic clocks, 1997 kind of epoch, every kind of molecules, some kind of vibrating bonds can be used, lots of different wavelengths from 10 micrometers to visible. Importantly, Venia Chebotayev was a big player in this, and some of his suggestions were coincident in time with the ones which Ted and I, following Ted, have pursued. Here is a discussion which needed some bottles about how are we going to measure these frequencies. And one of the things which the United States was able to contribute to this was a metal bottle with some particular kind of freon, which Chebotayev put into his overcoat and went through the airport security and back home. So here is a way of doing this. This idea was to notice the frequencies of these different things, and roughly speaking, they have the same gap between them. And so you can see some kind of strategy coming up where if you took this one plus this one, that's a little bit close to 2 times this one. So you end up with some little equations about this, and you're left with something which is not quite pocket change, but it's something which we can measure. And Kurogi-san had done some beautiful work making a comb, and he introduced a language of comb. He did it in the hard way, which was a microwave modulator, just 10 gigahertz, but it's relatively straightforward to go 10 times this, which is to say up to a few % of the light speed. But what we'd really like is a system that just plain works, and that this system should be gears with no chatter in them, and we'd like to start in the radio frequency domain, and we'd like to end in the optics. And as I mentioned, this frequency ratio is around 10 to the 5 or 10 to the 6, so the gear teeth are not quite to scale. Now here are these same molecular transitions, atomic transitions that we have, but now we're going to look in a different way. This is some things which, as far as the metrology community was concerned, these slipped in under the radar. It was a paper by Hench and his colleagues and by Chebataev in the same epoch that were pointing out the utility of pulse lasers, which pulse lasers to me meant that it had enough energy it could melt through a nickel, or it could erase the eyes off George Washington on a US dollar bill. But this actually was enormously important, and it really turns out to be the right way of doing it. So it's this completely surprising thing that if you have an impulse function in the time domain, you can use it to measure something which is completely sharp in the frequency domain as well. And the way to do that is to not have one of these time domain impulse functions, but to have plenty. So if they're coming in a completely regular way, then what happens is that some integrating instrument that can see many of these in time in order to get the Fourier resolution, it would see these all in phase at some particular wavelengths or frequencies, and it would generate some effectively comb of different frequency components. And so you directly can see that if you had the pre-knowledge of one of these comb lines, then you can measure a laser at a different frequency because you just count the comb lines. Now, the first implementation of this was a spectacular result from Ted's group with addition of some a little bit complicated auxiliary things. But nevertheless, 10th of April in the year 2000, they managed to use the comb physics, and perhaps Ted will explain this, to convert between cesium atomic clock and some optical frequencies. Just in that same epoch, actually a little before that, people were talking about nonlinear physics, and there was some wonderful postdoc, Janendra Ranka, perhaps a member of the staff by that time. This is the usual 125 micrometers fiber for telecom, but you'll notice that it's fabricated in a kind of weird way. It was made with little tubes, except for the center when they put these together for the stacking. They had a rod. So this is like the core of an ordinary fiber. The light's going to go down there, but it's too tiny, and so some of the light will stick into the holes. It'll be traveling inside this air-filled space. And what's important about it, and was shown in an absolutely shocking standing room only session at the Laser Engineering Conference in 1999, was if you put red light into it, its color gradually propagates through and changes in the spectrum. Now, this inputting light is always 100 million times per second. That's fixed by the laser. So this is, roughly speaking, white light, but it's periodic at 100 million times, so that will be a comb. So I was then, the next day after this session, get on an airplane and arrive at a conference in Europe. After that, due to Ted's generosity, I joined his group, And we spent plenty of long-distance money trying to get some of this magic fiber from our colleagues at the Bell Laboratories. It was a completely marvelous thing, and Ted and I could just see that this is really the starting of a new time. So this seriously nonlinear optical fiber, here's this again, this picture. Its properties that we use is that there's zero linear dispersion at some wavelength such as 800 nanometers. That has the physical consequence that this tiny pulse doesn't spread out. So if you smack it with this high intensity from some pulse laser, it just keeps propagating down, and whatever response it makes can add up. So when you put in a spectrum of some width after the fiber, it's expanded by a factor 5 or 10 or some. And it produces, indeed, a spectral continuum. Not quite continuum. This is actually 1 million lines. On the tabletop, it looks quite small, quite compact. Here's the edge of a microscope lens focusing into a little piece of fiber, and then the blue light is coming out the side. You can notice this is not too long a fiber because the piece which we approached the Bell Laboratories in a completely conscientious way, and we asked for a piece to be sent as a cooperation with a NIST. But the lawyers saw that this perhaps had value. We've had it in our store for 12 years. We have never found any use for it. But you want it, it must be valuable, so our answer is completely no. But by some method that I don't need to know, we obtained some piece, and we were frightened to use more than some small amount. So in the evolution of this laser, here's the output mirror, here's the return mirror. Every time we touch the mirror, we couple out some of this pulse. The important thing is that these pulses are so short that this envelope, which defines the pulse, compared with the wave of the high frequency variation, which we're going to use for our measurements, it's continuously evolving, and you can see this shape changing at the top, so that we have 2 consecutive pulses which have, in fact, a different shape. So thanks to Steve Kunda for this picture. So if you look in the time domain at the repetition of these, then there is more phase in this carrier wave per each pulse than you would have thought just based on the repetition rate. And that means that the comb is shifted a little bit. And our business then was to try to figure out a nice way to measure this. We called it a self-referenced frequency synthesizer, which is possible to take the frequency, including its offset, multiply it by 2 in a nonlinear crystal, and then we could compare that with a comb line where the integer was a different one. The lasers that one uses for this are originally based on Ti-Sapphire, which works in a marvelous way that in order to get through this gate, the laser cavity needs the high power of all the pulses to be added. We can change the wavelength a little of all of them by moving the mirror, or we can change it differentially by moving a mirror that's in a wavelength dispersed plane. So our first publication then had a few measurements for YAG-tuned laser. These are frequency offsets compared with what the metrology community thought the frequencies were. And it's interesting that practically the community was not so bad off. That, for example, the assumed uncertainty of this was 50 kilohertz, and here we are at 7 or something. The dispersion of these measurements in those days was some value, and this is basically limited by the standard we measured. So I'm coming towards the end. This result which we had was published, now 2 weeks later than the Max Planck guys, but we had one new capability which their system didn't have. That was that when I designed this locking system, there was a little click switch, and you could set it on 1 or 3 or 7 or 15, whatever you like, and this carrier to envelope offset phase would be registered by that. And that gave, if one made a comparison of the pulse which takes a short path with a pulse which takes a long path, so that's 2 pulses difference, then we would be able to measure this phase shift as a function, effectively, of my click step. So there was no doubt that one was dialing in the carrier to envelope offset phase. So this was sort of a time when the telephone was heated, and we had a publication from Ted's group, 10 April, from us, 28 April, and then finally from the combined team of the JILA guys, the Lucent guys that made the supplied the fiber, and the Max Planck team, 29. So this is a case where interference is quite there, and I choose in interpersonal relations to try to have it be a positive interference. Optically, it makes good comb lines, and in the laboratory, it makes fantastic time. We enjoyed the presence of this wild man from Garching many times. So here's the measurement of the absolute frequencies in the modern times, this PTB measurement from Germany, 96. Some other measurements by Kurogi comb. And then here's the start of this modern epoch of 10 April, 28 April, 29 May, 12 June, 7 July. Look at how many absolute frequency measurements of how many different things are done in this short time. Now that already teaches you that it doesn't need 10 years anymore to measure an optical frequency. These teams in lots of different labs. So now we have the picture that, well, there's lots of different candidates for high performance. Which sign are you going to show me next? The 1 minute or the 5? So the calciums, mercury, as one of the candidates which can have not just one ion but 1 million atoms. Junyi's group is working on strontium. I, again, like this pretty good tech because the iodine system can be made in the format that can go under your airline seat. And if we did this fiber business, the laser business for the femtocomb as a fiber, so everyone has such an idea. And in fact, some colleagues of the Max Planck even have this commercially. Well, let me just say a couple of more things. You can have a standard someplace, but the customers are probably not there. So this shows that our standard is not so bad. We measured it against the NIST, but our two laboratories are not in the same place. And so we have to transfer by fiber. And if you have your own independent standard, you pay what feels like a pretty large amount of money, $66,000 for your own cesium clock, but it's not near the performance as the NIST has for their hydrogen maser, which is the life work of people over 15 or 20 years. Here's what the performance could be in green. We prove that by having 2 of these iodine systems in our own lab. And now we send the light over a fiber as optical signal and measure it against some wonderfully performing work of Jim Berkowitz for cavity. And we see like we're mostly on the picture to carry away from this is the black dots are good, that's optical measurement. Red dots are not so good, that's microwave measurements. Here's the fiber network in Boulder that goes from the university to the JILA to the NIST. And if you send your signal on the fiber, of course, there's changes happening, so your bright monochromatic signal comes out with a finite width. But if you send it there, let it come back, then we can see what happened to it, and we can take half of that and put it on as a correction in advance. So this blue guy, and then on a magnified scale, shows you that we can basically have the same information after a few kilometers. I think the last physical thing I'd like to show you is about the exquisite control that's possible. This is going to be important if you have a laser that makes these pulses, and those are at one color. Another laser that makes these pulses, and then with some phase measuring system, you can adjust them to be closer together, closer, and finally nearly overlapped. And in such a case, if you look for the double frequency, the other one, and in this center place is where you'll find the sunbeam. So these pulses have to align within around 10 femtoseconds, otherwise you don't get any sum frequency because they're just not there at the same time. You can run this at different frequencies, 100 megahertz and 90 megahertz, for example, and now it's only every 10th one that aligns. You can synthesize new pulses, some kind of autocorrelation function for one laser, for another laser. They have a black spectrum and a green spectrum with 50 or 80 nanometers as the difference. If you don't do any locking, then you just add the two spectras. But if you make phase coherence between them, then of course there'll be phase interference. And if you look in autocorrelation mode, you will see by a single pulse, they're not so interesting. If they're not synchronized, they're synchronized but not phase locked. And finally, if you phase lock it, it does what you'd think. There's more spectrum, so there's less time. So it's just completely marvelous. So the short summary of this is that the tools are now in place. These little boxes that have connectors on them plugged together. Some of the connectors are microwave, some are optical. And you can change what time delay you have. That would be fun. One last thing which I will just say that we were quite pleased with is a new mounting strategy so that you can have 1 hertz wide lasers, sub-hertz laser line width on a tabletop. So I come to the end. What's the opportunities? Well, this reference comb is some gearbox, and it can work completely marvelously in a standards laboratory, and with effort of these marvelous friends of Ted and me, that you can even buy these things now. It's simpler and better. Where physics, that's how I started. What physics do you want to do? Some people are interested in the height of the oceans and in mass condensations on the Earth. They used a millimeter wave interferometer, and I'm asking, please let's do this with optics the next time. The LISA gravitational wave astronomy is completely built on the tools that have been built up in this 25 years of successful program. One of the projects which I think is totally cool is measuring curvature in the local space, and the way that that shows up in the newspaper and in the funding is that you can find planets by finding that light is not coming to you in the way that you thought. I like this subject of Michelson-Morley experiment or Kennedy-Thorndike experiment because we slipped in one on you. We changed from a wavelength standard to a frequency standard, and perhaps there's some subtleties about that. And as well, when we look into the early universe, we find that it's not at all homogeneous. It has strings. And so it's quite interesting to look with plenty of digits at whether local Lorentz invariance is there. And of course, with the clocks, we can look for the changes of the constants or the equivalence between hydrogen and antihydrogen. The team as it exists now, a retired guy comes in, I think I heard 10 and 12 a.m. from Roy Glauber. I try to come in 10-ish sometimes, but not every day. June is running the whole store, and we're often lucky to have Professor Ma with us from Shanghai or from Paris, depending on where he was. This cooperation that I mentioned is occurring here in a standard kind of way. I promised that we used more paper than this for the night's discussion. We started when it was quite light in this kind of outdoor science discussion area. The people that you don't necessarily know is Ron Drever, the co-inventor of the stabilizing method, and Thomas Udom, one of my favorite boson colleagues, to be either gathered around in Boulder or gathered around in München. And finally, many people have given advice to me over my time, and I can offer just a tiny bit of advice on the topic of building a group career. The most important thing which you will do is to establish a lifelong bond, in our case, 47 years of formal association. And I thanks to this lady for her tolerance of a few late nights and missed dinners. I'm quite happy about the some responsibilities come, and there's space for you can. Future is what I like to look about, see what has happened, what will happen, and I think I feel quite happy with a young guy at 2 years who finds that a mouse is the most interesting kind of toy. So anyway, that's the story from Lake Wobegon. Thank you.